This is Diesel Talk. Welcome to episode 8 of Diesel Talk. So in this episode we have 4 questions we're going to be talking about. One has to deal with diesel engine horsepower and why it appears to be a lot less than a much smaller size gas engine. We have a question on why a truck engine won't start. We have a question on RV engines and why they tend to overheat. And then we had a question on kind of the emissions changes to the engines over the years. Okay, pretty good questions this week. Also, I'd like to say thank you to everyone that's donated over the last couple months since I opened my PayPal account, which is adeptape@yahoo.com. I've spent pretty much all that money that's been sent to me on the making of hopefully better videos. I've updated the webcam, so that makes making the videos easier. I've obviously updated. I've got a new mic, Audio Technica 2020. I've got a mic stand. I've got a pop filter. I've also updated my software. I actually bought software, so I got Adobe Premiere now, which will make making the videos easier, and I can change a lot of the parameters and, do a lot more customization of the videos. Okay, so thank you to everyone that's donated. I do spend the money on the channel. Now on to the show. All right, so Steven asks, and he's referring to the video about diesel engines and why they can last so much longer than a gas engine typically. And he says it's about the amount of power to displacement. It's much more lower compared to a gas engine. A 15-liter cat diesel only puts out 500 horsepower. A Corvette engine also puts out 500 horsepower, but it's squeezed out of less than half the displacement. The diesel engine parts are also much less loaded compared to the Corvette. So let's compare a MXS C15 to this Corvette. And I looked up, it's an LT1 Corvette engine, not the Z06, which, costs $100,000 on the normal Corvette. And they make 460 horsepower, and a Cat MXS, the highest rating using all normal Cat parts and just the flash file, is 550 horsepower. And okay, let's compare the two. What are the differences? Why can a gas engine make so much more horsepower than such a larger diesel engine? Well, the first main thing is RPM. So that diesel engine is making 550 horsepower at what RPM? 1800 RPM. That's incredibly low. Now let's look at the Corvette. Let's look at the Corvette torque and horsepower curve. So the Corvette makes 460 horsepower out of 6 liters, yes, but at 6,000 RPM. Let's compare the RPM at 1800. Look at that. It's less than 100 horsepower. So even though it's less than half the displacement, it's making less than 1/5 of the horsepower of the diesel engine at the same RPM. Now the holdback for the diesel is it cannot reach 6,000 RPM. If it does, that sucker's blowing up because they overspeed usually about 2,500 RPM. So, okay, they make comparable horsepower. If that's really true, would you hook up the Corvette and the truck and do a tug of war? No, you wouldn't. And that's not to disparage the Corvette. It's purpose-built for going fast. But that truck would rip the powertrain right out of that Corvette. And the reason is torque. Most automotive engines produce similar torque numbers to their horsepower numbers. The horsepower and torque on the Corvette are only off by 5. So foot-pounds of torque are 465 and horsepower numbers 460. And they're both at much higher RPMs. Now, the diesel at 1200 RPM makes 2,000 foot-pounds of torque. So roughly 5 times the amount of torque that Corvette can put out at a much lower RPM. And that's really what you need to look at when you're looking at, power numbers. That truck can move a lot more weight, a lot more efficiently because it has much higher torque. Torque is the ability to turn the wheels. Horsepower is not a real good indicator of the ability to move items. It's more of just a math calculation as to the amount of work that that engine could produce. But one more thing, how often is that Corvette at 500 horsepower? Are you driving to work at 6,000 RPM? Are you going up a hill at 6,000 RPM? Because that's the only time it's making 500 horsepower. Typically, you're probably going to be in the 2 to 3,000 RPM range just driving down the road, and that Corvette's only putting out maybe 100 horsepower to just get it down the road. The difference is that diesel engine is built to be loaded nearly all the time. If you're pulling a hill or got a heavy load, you're pushing closer to that 500 horsepower nearly all the time, and that engine will last much longer. The Corvette engine is not built to run at 500 horsepower the entire time. So if someone brings up horsepower, just, keep these things in mind and say, oh, okay, is that true? Well, do you want to hook up to my truck and test that out? Okay. Just trying to clear up some misconceptions on horsepower. Okay, thanks. Okay, so some guy asks, do RV engines overheat more than most other diesel engines? If so, why? In our shop right now, there's 3 or 4 RVs, and most of them are in there for overheats, and it's November. So yes, I would say we see more overheats with RVs than typical truck engines. And there's several reasons for this, and going to kind of talk about why that is, or at least why it seems that is. So one thing is that RVs typically have the engine in the rear. And if they're a rear-mounted radiator, you're going to get much less airflow through them naturally. Because as a truck, if your radiator's in the front of the engine, you're going to get all that air pushed through, and then the fan's going to be on or off depending on how hot it is. On an RV, typically the fan's on all the time. And the heat from the engine then gets pushed through the radiator back and then out the back of the RV. So there's less natural airflow going through the radiator, and it has to be forced through the fan. But it also has to go through the fan shroud. Now, what causes a lot of overheats is your blow-by. Your blow-by is oil fumes, which on a truck or even on an RV comes typically off the valve cover or off the side of the engine, and it vents to the atmosphere. And on a truck, your air is getting pushed through the radiator, then past the truck, and it'll pick up those blow-by fumes, and it'll push them onto the truck. And, that's why a lot of the time you'll get like a light oily residue and some road grime on your transmission, your tanks and stuff, because you're getting a little bit of blow-by on there, and oil makes dirt stick to it. So on an RV, those fumes get pushed from the engine into your radiator and your CAC, and the oil that gets on there is going to pick up and attract dirt. So all the dirt starts getting stuck to that, and it blocks a lot of your fins on your CAC and your radiator. So you get a reduction in cooling ability. And the problem is usually you have your radiator and then your CAC stacked in front of one another. So it's really hard to clean that out unless you get them removed and cleaned. Also, the radiator in an RV is typically lower, closer to the ground. So it's more likely to pick up debris, rocks, things like that can damage the RV. RVs tend to typically have the cooling system serviced less often as well. So they'll get more deposits internally, and they sit for very long amounts of time. So sediment will settle a lot longer. You can get, more scaling buildup if the systems aren't serviced as much. Let's see. They also have more plastic components, such as the expansion tank. And opposed to most trucks, seemingly have some sort of steel tank, which is less likely to rupture or leak. The plastic tanks can. So we have one in the shop right now. It blew the expansion tank up and lost all the coolant, caused an overheat. It's fairly common, actually. And the expansion tanks are pretty expensive. You're talking $300, $400, $500. I recommend if you do have an RV and you have a problem with the expansion tank, get a metal one made. Either steel or aluminum. You can have it made at a radiator shop, or sometimes the plastic replacement updates to a steel one. If you're having problems with those, it's a good idea to get that changed before it blows up on the side of the road. Another problem with RV overheats. Some RVs don't have a rear radiator, they have a side-mounted radiator, which means the fan drive isn't off the engine, it's typically hydraulic, and a hydraulic fan relies on a PTO. So then you have control valves and you have a PTO. They have a lot of problems with those because sometimes the valves will fail or the PTO will fail and you won't get as much fan speed. And since the radiator's sideways, you're not getting a lot of airflow force through there at all. So those can give you a lot of issues. Also, RVs have higher horsepower ratings for standard engines. So if you have a C7 in a service truck, it might be rated at 250 horsepower. In an RV, that's usually rated at 350 horsepower. So if you have more heat, if you have more power, it's going to make more heat. And more heat, overheat. So that's kind of the things that can lead to RVs causing, they seem to overheat more than comparable sized trucks. Okay, that was a good question. So next question has to deal with a clip in the last video. And Gregory asks, so why did the C15 not start in the video? Or why didn't the C15 you showed in this video not start? And what he was referring to is the C15 where I had the inductive voltmeter, and it was showing that the injectors were trying to fire, but it wouldn't start. I did a lot of troubleshooting on this truck. I checked, this truck had been rebuilt in the field by the owner of the truck in a dirt lot, basically. They'd reused the injectors. The mechanic that did it, he was pretty knowledgeable, and everything I could check he had done right. Cam timing was right. I didn't see any damage to the crank or cam position sensors. The overhead appeared to be okay. Had good fuel pressure. ECM was firing the injectors. I was kind of running out of things to check. It would start on ether, so you knew the valves and everything were at least opening and closing at the right times. And what it ended up being is, since they'd done it in such a dirty condition, he had all the injectors out in this condition for several days, and the injectors had actually failed, from what I could tell, from dirt and debris getting in the injectors. And all the injectors wouldn't fire. They had fuel pressure, they had electrical signal, and they just wouldn't fire. Ended up replacing the whole set, all 6, and truck fired right up. Ran good. So it just goes to show you that you want to keep the fuel and your injectors as clean as possible. If you are removing injectors, you're going to reuse them, especially in a dirty condition. Get them, don't just wrap them in a rag or something. Get them in an airtight container, big Ziploc bag, something like that, because they're like $600 each, and replace them. All right, but that was a good question. So our final question's from Norwood. And the last video, he had mentioned that he wanted to see kind of what CAT's progression through their after treatment processes were. He says, that was awesome, mate. This video cleared up a lot of my confusion on the CAT nomenclature. As far as the question I have on CAT versus Cummins, I mean the specifics of the CAT after treatment system, like from start to finish of the CAT after treatment process, and different versions on the medium and heavy duty engines. So I'll try to answer that as best as possible. Hopefully I'm getting the question correct. So, differences between the CAT engines. Well, I'll start with the heavy duty. So heavy duty being C13, C15. On the older, let's start with 3406Bs. They were strictly mechanical, no emissions. Then they went to the 3406E, also no emissions. Then they went to the C-15, no emissions, electronic engine. And then they started with the ACERT C15s. And these they didn't really have hardly any emissions other than, they have a fuel ratio control, which is supposed to never allow more fuel than air, which causes black smoke. Then they started having the electronic controlled wastegates. And then they went to the twin turbos. So your BXS, your MXS, and your NXS engines. And what they had were IVAs, and also known as VVAs. And they were basically jakes for the intake side. And what they're supposed to do is release some of the high pressure conditions out of the cylinder at different times to reduce nitrous oxides, because nitrous oxides are made by real high pressures, lots of oxygen, little fuel, high heat, which is diesel process, and you get lots of nitrous oxides, which are supposedly ozone depleting. And then when they went to the regen system, they also have the IVAs, also known as VVAs, and my next video is going to be on IVAs actually. And then they added all the regen stuff. So what did they add from the previous model year? Well, they added the ART head, the fuel enable valve, pilot and fuel control valves, pilot and fuel pressure sensors. They had the fuel enable valve. They added, let's see, the secondary air circuit, secondary air control valve, the CGI tube, CGI mixing valve, CGI sensor, secondary air sensor, ARD flame temp, ARD outlet temp, and then you have your DPF with a DPF differential pressure sensor and DPF inlet and outlet temperature sensors. As far as the base engine, they didn't change a lot other than the injectors went to a dual solenoid setup, so the plugs are different on a SDP opposed to the previous model year. It's a 4-pin plug opposed to the bolt-on 2-pin style. And the same for the C13s, pretty much. C15 and C13s, they added the same stuff. Now from the C7 and the C9 up to the C7S and C9S, which were regen engines, they added a whole bunch. Because they were HUE systems, they didn't really have any emission stuff on them. And then they went to a common rail setup, so you changed your high pressure pump. You added the common rail itself, common rail fuel lines, quill tubes, new injectors. And then as far as the after treatment, they added all the same after treatment stuff as on the C15s. You know, your CGI mixing valve, secondary air circuit, the ARD head, combustion housing, DPF. They also had, you know, they have the spark system as well. They also had a purge air line on the C7s and C9 that was supposed to purge the ARD head with pressurized air. That really don't work. On the C15s, they had a heated nozzle design, which seems to supposedly work better, although the ARD heads still only last about a year, it seems. And then the process really, you know, the CGI is the same as EGR, it's just CAT's term CGI. It's supposed to reduce your fresh air intake from strictly fresh air with high oxygen content to inert air with less oxygen. That's supposed to reduce nitrous oxides. They're also running the IVAs. And the after treatment process from start to finish. So if you've seen my video on regen, you kind of know the process, but ECM monitors your DPF. When it thinks the DPF's full of soot or getting there, it'll initiate a regen. The secondary air circuit kicks on, makes sure that it's working. It forces pressurized air into the ARD head. The ARD head then turns on the fuel enable valve, which sends high pressure fuel to the pilot control valve. The pilot control valve then supplies high pressure fuel to the ARD head. That atomizes the fuel inside the ARD head combustion housing. Then there's the spark circuit, which kicks on, supposed to light the flame inside the ARD head combustion housing. That in turn increases your exhaust temperatures to 1085 degrees, which then is supposed to heat up the DPF enough to turn the soot to ash and burn it off. At which point, it's supposed to drop your differential pressure back down, and then your ECM will see that it's done a successful regen. It'll log a 310 code, and you will be on your way. That's a successful regen. Okay? So that'll be all the questions for this week. If you have any more questions you'd like to ask in the next video, just leave them in the comment section, and thanks for watching. Okay, bye.